This is part of the specification which you need to know when revising for your exams. And I would recommend and encourage using the specification to revise from, because it contains everything that you need to know. In this video, we're only going to go through the first 3 points of the first part of the specification 1A, states of matter. So we'll look at this part of the specification, understanding the 3 states of matter in terms of the arrangement, movement, and energy of the. Okay, I'm going to give you 5 minutes to complete this. You may pause now. Okay, so here are your answers. I've asked you to use only 9 particles only. That's just so you can see the difference in volume of the gas. So the gas takes a lot more volume per part for every, even though it has the same number of particles. While solid and liquid, they take up roughly the same volume. Your solid moves. It just vibrates on the spot, so it doesn't really move away from that spot. It's fixed and it has low kinetic energy. It's just, each particle is just vibrating. If you increase the temperature, you increase how much they vibrate from their spot, but they never really leave their spot. If they leave their spot, then you have broken the intermolecular forces that are holding them together, and we're going to look at intermolecular forces a bit later. Your liquid, however, that moves a bit more. So your liquid the particles move around each other. I like to think about liquids, particles in liquids, similar to balls in a ball pit. So they're all together. You can't compress them really. So they're incompressible. If you get a hydraulic press on both solid and liquids, they won't really compress. So there's not much space in between the particles for the other particles to move into. Whilst gas, on the other hand, if you get a hydraulic press and just press it down, it can move. And this is why it's not very good using it for like hydraulic brakes or anything. And this is why liquids are used for like, hydraulic brake systems, because if you push down on one part, so if you push down on the brake lever, the other part, the part near your brakes or near your disc, will actually move the same distance that you've pushed, because liquids aren't compressible. So your particle movement, we've just went through that. Your particle arrangement, your solids are closely packed together. There's no space in between them. They're arranged regularly, whilst gases, liquids and gases are arranged irregularly. They are irregularly arranged. Liquids are closely packed too, like solids. They can't be compressed, as I said before, whilst gases, they're spread out. There's a lot of space in between them. They can move into that space. The amount of space in between the particles also changes depending on temperature, depending on pressure, and things like that. So the gas's volume can change, whilst the liquid and solid's volume is pretty much fixed. Your shape, your solid takes the shape of the container. Sorry, it doesn't take the shape of the container. It's got its own fixed shape, and that's because the particles are held together by intermolecular forces, and they don't move. They've got their own shape. Liquid, on the other hand, the intermolecular forces are a bit weaker, so they can still move around each other, but the intermolecular forces hold the particles together, but not in a fixed shape. So they're not as strong as in solid. Whilst gas, there's no there's very little intermolecular forces in between them. There's still some, because they're still held together in somewhat, but if you leave them in a room, they'll just spread out, and then they'll be so far apart that there won't be any intermolecular forces acting in between them. Your volume, we just went through that. Your volume of your gas varies depending on temperature, as we said before. And density now. So density is just how many particles you have per space or per volume. So solids have a very high density. Liquids, on the other hand, they have slightly less density than solid, but they're still highly dense. And you know that they're slightly lower than solids because all substances in their solid form, they sink on their liquid form. So if you had molten metal, it would, if you had a solid piece of metal, it will sink if it was in a molten, if it was in its molten form. So you know that the solid form is higher than its liquid form. Gas is less dense, and we've already gone through compressibility with the hydraulic presses at the top. Okay, our second point, we're going to move to understanding the interconversions. That's just the changes between the state of the three matters, and that's in terms of their names. So that's just like melting, freezing, that type of stuff. How they are achieved, and that's with breaking. So we're either breaking or making intermolecular forces. I'm just going to put IF there, but you'll see what I mean later on with the graph. And the changes in arrangement, movement, and energy of the particles. Now we've just gone through the arrangement, movement, and energy of the particles. I'm going to give you about 4 minutes to complete the diagram below. You can pause the video now. Okay, so here are the answers. From your solid to liquid, your state change here is melting, and that therefore gives you the melting point. Now it's the same, melting point is the same whether you're going from solid to liquid or from liquid to gas. It's still called melting point, and that just makes it a bit easier for us. And you'll see going from liquid to gas, that's water to steam, that's called evaporating or boiling. Now I think it's probably better to call it vaporization, because that is easier, and it doesn't allow you to get confused between these two terms, evaporating and boiling, because they are slightly different. They are slightly different, but we use them interchangeably when in fact they're not. So gases, when they go from gas, when substances go from gas to liquid, that again, that's its boiling point, and that is called condensation. Now B, with our subliming, with B going from solid to gas, that is called sublimation, and iodine does that very, very well. So iodine crystals turn straight into a gas, and that's actually quite a nice experiment if you want to look at that. But also dry ice, so dry solid carbon dioxide, that turns straight into gas, and that's our basis for like stage smoke or fog, anything like that. And that's just because you're solid or dry ice, that turns straight into a gas, and that's your fog there, okay, in movies and things. The opposite way is deposition. So your gas turns into a solid, and that's called deposition because I guess solid is being deposited, or it looks like something's being deposited. And that, the clue there is in the name, that could really help there. Okay, so here's a graph which shows you what happens in these different state changes for the energy. So what happens to the temperature as we change state? Now it's quite weird because the temperature doesn't increase uniformly as heat is added. The temperature doesn't increase uniformly, and I'm gonna explain why, and that's all dependent on the intermolecular forces. So here the state is solid on that part of the graph. Here the state here is liquid, and here the state here is gas. Now as heat is added, your solid starts to vibrate more. It starts to get more energy, more kinetic energy, and the particles vibrate more and more until they can't vibrate no more. So when they can't vibrate no more, this is where we get this flat line. The temperature stops increasing. So as the particles vibrate more, the temperature increases. So temperature and vibration of particles are actually linked in some sense. And then here, as we have this flat line here, the particles stop moving. What's happening here is intermolecular forces are being broken. So IF, I'm going to use IF here. Intermolecular forces are being broken, and that's the same with every flat line. So as you go from liquid to gas, again, intermolecular forces are being broken. Now, if we did this the opposite way round, so if we did this is a heating curve, if we did a cooling curve the opposite way round, this would be the same thing, except for intermolecular forces aren't being broken, they'll be made. Okay, now this is what I was talking about before when I talked about the difference between evaporation and boiling, and why it's probably best to just use the word vaporization instead. Even though it sounds a bit of an American term, it probably is better to use. So the difference between evaporation and boiling, I've got some statements here which I'd like you to rearrange and put into the right columns. Now, some of these sentences can be put in both columns. You can just put them in the middle. I'll give you 5 minutes to do that. You can pause now. Okay, so these are the answers, and I just wanted to talk about some useful process, why evaporation is useful as a process. So evaporation allows us to dry our clothes without boiling the water. It allows our skin to cool without the sweat being boiled off. It's also important for lots of other processes like super glue. So if you have a cut and you super glue your cut together, which they used to do in the olden days, then the reason why that super glue dries is because the water from the glue is evaporating. Now you'll see that the water doesn't need to boil for water molecules to turn from liquid to gas. So it's a very useful process, evaporation. Boiling, on the other hand, water particles do need to reach 100 degrees Celsius for this to happen. I'm just going to put next to evaporation that this happens at all temperatures between 0 and 100 degrees. 0 and 99, isn't it? 0 and 99 degrees, or sorry, 1 and 99 degrees. Okay, and then boiling, this happens at 100 degrees Celsius. Okay, and this is a lot quicker. And you can see some of the differences in the paragraph here. And this is useful because it allows us to cook, it allows us to harness energy via generators and turning a turbine and things like that. So it allows us to turn water into steam, and we can harness that steam and transfer its energy into something more useful, to kinetic energy or any other type of energy. Okay, in the next part of the specification, 1.3, we're going to be explaining why solutions get lighter when you dilute them, and also why air freshener spreads through the room. To understand this, we have to look at the definition for diffusion. Diffusion is the spreading out of particles from where they're in a high concentration. So I'll just draw the particle diagrams underneath here. So where they're at a high concentration, which is below, to where they're in a high concentration. There are lots of them in a certain volume, to where they are at a low concentration, so a lower concentration. So we go from high to low here. So diffusion is the natural spreading out of these particles. So after a while, your particles will begin to diffuse. So let's rub out some of those. They'll begin to diffuse until they are evenly spread out. So you've got an even concentration everywhere. And this, in here, the particles are still moving. So even when they are evenly spread out, particles are still moving. And diffusion is actually some evidence of movement of particles. So there are three factors which affect the rate of diffusion. And the first factor we're going to look at is temperature. So diffusion happens quicker when warmer, so when the temperature is higher. And if we have the particles, when in a higher temperature, there is more energy. Therefore, the particles are moving around more if they've got more energy. Therefore, the rate of diffusion is quicker. And that's the opposite if there's a lower temperature. There's lower energy. Therefore, the particles are moving less, and there's less diffusion, and the diffusion is slower. Okay, the second factor which affects the rate of diffusion is the state. So either gas or liquid. In gases, diffusion happens quicker because particles are more spread out than in liquid. Therefore, there are less collisions and particles can travel further without colliding. So it all depends on the space in between the particles. The third factor which affects the rate of diffusion is mass, the mass of the particles. So diffusion happens quicker if particles are lighter. And that's because lighter particles travel further, they travel quicker and therefore further. They therefore diffuse quicker. So if you look at this example here, in this apparatus, we have aqueous ammonia, which is NH3. And if we look at the MR, or the molecular mass of NH3, we have 14 plus 3, which equals 17. That's the mass of one molecule of ammonia. Then the mass of hydrochloric acid, so the MR of our hydrochloric acid, is 1 plus 35.5. You can just look at the molecular masses in the periodic table. That equals 36.5. So you can see that hydrochloric acid particles are heavier, therefore they're going to move slower. So looking at our experiment here, we can see that the aqueous ammonia has moved quite a lot further than the hydrochloric acid. This experiment is quite good, is useful, because the product is a white solid, so the product is visible. We can see this, and this shows us the distance that both these particles have moved. And you can probably predict that because hydrochloric acid particles are twice as heavy as ammonia particles, they've moved twice, roughly around twice the distance. Okay, just a recap of the 3 different factors which affect the rate of diffusion. That's temperature, first one. Diffusion happens quicker with increased temperature because particles have higher energy, therefore move quicker and therefore diffuse quicker. Second factor is state, the state that it's in. So diffusion happens quicker in gases than in liquid. That's because particles in gases collide less frequently, therefore travel further, and therefore diffusion happens quicker. Your third factor is mass. Diffusion happens quicker if the particles are lighter. That's because lighter particles travel quicker, therefore diffuse quicker.